All right, guys. So wanted to give an example with a rolling problem. Now, this is not going to be in the problem set. This is just the problem that I'm doing. So what you have is you have this wheel, right, which is basically moving. You're also given that the mass is 18 kilograms and it has a moment which is applied to it and is just left on this, and you're asked to find what the angular acceleration is and what the acceleration of the center of gravity g is. Now whenever you have a problem like, oh, and also there is friction, right? So you're told that mu s is equal to 0.3 and mu k is equal to mu s is 0.33 and mu k is equal to 0.3, right? So when you have stuff like this, you can have slipping that's happening, but if the frictional force is strong enough, then there's going to be rolling that's happening. So the way to solve a problem like this is that you assume that rolling is happening, find out what that force is going to be at the point of contact to make rolling happen, because that makes solving the problem a little bit easier. And if that force is less than your force due to your static friction, you're good. It's rolling without slip. But if that force is larger than the force due to static friction, then your disc or your wheel or whatever you're looking at, cylinder, is slipping while it's rolling. And then you have to go about and solve the problem a different way, all right? So to start off with, let us assume slip. Right? And when I'm looking at the free body diagram for this guy, I have my normal force, I'm going to have my weight, and now the key thing is that when you're assuming rolling without slipping, you can assume the direction of the frictional force and it's going to work out. But when sliding is happening, you kind of need to know the direction in which slipping is going to happen. So for this specific case, because we're not sure, we're going to try to figure out intuitively what direction the friction is going to act in. So in order to do that, you need to see that impending motion is going to happen because this is rotating this way. So this point wants to move in that direction, right? So that means that friction is most likely going to act like that, right? And then, so this ends up giving you the free body diagram. And if you want to look at the kinetic diagram, I'm just going to draw it to the side over here. The body is obviously going to translate in, it's going to move that way. So it's going to have an AGX term. So that's basically what we need to find. And it's going to have a rotational term. Let's say that that is IG alpha. All right. So now we assume slip. And when we're assuming slip, I'll just put my frame of reference kind of weirdly like that, just so that because the friction is in that direction, just to keep stuff positive, right? So I'm looking at forces in the x direction, right? So the one force I have in the x direction is the friction force. So you see that's the one which is causing the motion to happen, right? So that's equal to m from my kinetic diagram, AGX, right? So now my mass is equal to 18 kilograms. So that's 18 times AGX. All right. So one equation for two unknowns over here, right? So F is unknown and AGX is also unknown, right? Now, if I look at my force in the y direction, right, what do I get? I have N minus W, and there's no motion in the y direction, so that's just equal to 0. So from here, I see that my N is equal to the weight, so that's just equal to 18 times 9.81. And everything is good because we're in SI units, so that's equal to 177 Newtons. So that's my second expression. And here I have my third unknown, right? So now I need two more, I have three unknowns. So let's see what happens when I look at the moment. So now, because rolling is happening, I can look at the instantaneous center of rotation, so the point O over here, and take moments about that. And that is equal to IO, so the mass moment of inertia about the point O times the rotation that's happening over there. So the only moment that's being applied right now is equal to this 80 Newton meter moment which is happening, right? So let's just say that that guy is positive, and that's equal to IO times alpha, so that's just equal to IG plus m times rg squared times alpha. And ig, I know the radius of gyration, so that's just going to equal m times kg squared plus rg squared times alpha. And all these three terms are known. I know m, I know kg, and I know rg, right? Because kg is 0.3 and the radius is equal to 0.5 meters. So if I do the math there, AT is equal to 18 times 0.3 squared plus 0.5 squared times alpha, and that turns out to be equal to 6.12 alpha, right? And from here I see that my alpha is equal to 13.1 radians per second squared. Now I plug this guy back into expression number 1. Before I do that, so that gives me what alpha is equal to, but I still don't know the relationship between AGX and alpha, right? Or do I? I do, because rolling is happening, right? So I can say that because I'm assuming rolling without slip, AGX is equal to what? Is just equal to alpha times RG. So from here, my AGX just turns out to be, doing the math, get 6.54 meters per second squared. All right. Now I plug this into equation 1 and I see that my force comes out to be equal to 118 newtons, right? And now if I look at my maximum force of static friction, say mu Sn, that guy is equal to 0.33 times the normal force, which is 177. That turns out to be equal to 58.4, right? So this force of friction that's needed for rolling to happen is more than the force that the static friction can deliver. So therefore, slipping, rolling without slipping is not happening. So this assumption was, I was saying, assuming rolling without slip. So basically what this means is that there is slipping. Okay, so now that kind of changes things up a little bit, because I can't use this expression over here and I need something else. I need an alternative fourth expression, right? So now just getting rid of all this stuff. These two expressions still apply, but I can't take the moment above the point O because it's slipping. So let's, for convenience sake, let's take the moment above the point G, and that's just equal to Ig times alpha, right? So the moment above the point G is what? I have my applied moment, which is the 80 Newton meter term, and then I'll have a moment due to this frictional force, right? So it's going to be minus, right? So minus F times 0.5, and that's just equal to Ig alpha, which is just equal to m times kg squared times alpha. So that's just equal to 1.62 alpha, right? So that gives me 3 expressions, but again I have 4 unknowns, right? So where's that last term going to come from? Because we're now solving the problem with slipping actually happening, you can say that the force of friction is just equal to mu k times n, right? So 0.3 times your normal force, so this comes out to be equal to 53.1 newtons. So now I can solve this whole problem to say that my acceleration, which is in the x direction, that scalar is just equal to 2.95 meters per second squared, and that the angular acceleration is just equal to 33 radians per second squared. All right. So when your slipping is happening, you can't take the moments above the point O, take them about the center of mass, and use your kinetic friction to find out what your force of friction is going to be equal to. Thanks.